This video is an introduction to GIS. GIS is the foundation of location analytics. GIS doesn't always hold a strict environment, whether it's a particular software or a particular strategy, but really what GIS is represents that entire foundation. We'll cover that. So GIS represents Geographic Information System, or if you have more than one GIS, you can have systems. Geographic relates to a spatial component, something that has a location, some specific spot, and it can be a geometry as well as a geography. So it could be a shape that represents an area or some volume, some vector. It can have a relationship to other geometries, creating a tapestry of relationships that are spatially oriented. Information is the tabular component. Think tables, right? From spreadsheets, from databases. They represent attributes as descriptors. They represent numbers. And a lot of times it just gets to traditional analytics. System is what puts these two together, which takes the traditional analytics, assigns it to a location, and now we have a new dimension of thinking and a new leverage on how we can organize our data. This linkage happens really through database relationships and then creating strategic images in order to present that depth of analysis, whether it's quantitative or qualitative. So our geometric representations are simple. We have 0 dimensions. It's just a point. One dimension is a line or an arc. It is possible to make the argument that this could also have something representing a function, right? So maybe if you had f of x, had a function that looked like this. We'll stay away from that simply for the sake of just keeping this a digestible understanding. And then 2 dimensions, we have polygons and circles. They have length and width, and we can calculate area. We can calculate perimeter if we needed to, right? And after 2 dimensions is 3. So we have polyhedrons, spheres, and you can again have irregular shapes that use this 3 dimensions. But again, just keeping it simple. 3 dimensions represents length, width, depth. And we can obtain a surface area and we can obtain a volume. Now beyond this is actually 4 dimensions. You can have multiple dimensions past that, but we'll just stick with this idea of the 4th dimension being a time variable. And this is movement or displacement. Somehow this geometry, somehow this data changes over time. Since points have no actual tangible concept, they're represented by some coordinate, and it cannot be physically observed. So we represent it by a substitute, whether it's a circle, X marks the spot, or some sort of clever graphic, and oftentimes those are strategically placed. We refer to this as symbology, what symbol is going to be there. Of course, arcs and lines, they are 2 points that are connected by a curve. This is represented by x1, y1, z1, for the first point, and then x2, y2, z2 for the second point. And then there's some radius r for curvature. So mathematically speaking, we have r is equal to infinity. We end up with this straight line, right? And then if r is less than infinity, right, then we end up with some form of curve, right? Most of the time we're looking at something that's a little more usable than this, so we don't necessarily say r equals to infinity or whatnot. We'll just say lines and arcs, or lines and curves. Now these also have no width. They have a length, but they have no width, so oftentimes we'll just represent that width in a strategic way. So here's how the computer sees it, and this is why we go through that whole point of saying that there's an x1, y1, z1, x2, y2, z2, and a radius value, is because you are computing in your head what that might look like, how that might work. But the computer needs something very specific to work with. And if it's not directly put in, it will be translated to something that looks like the following. A line has length. If it has r of infinity, or if it's going to be a straight line, then it uses this straight line formula, right? Most of the time we'll see this without the z variable, right? So it's just cut off right here. But if we're working in 3 dimensions, then we'll keep that. And then if it's an arc, the computer says, oh, here's x2, xy, x2, y2, z2, here's x1, y1, z1, and there is an r value. Let's go ahead and calculate what this L is here. And vice versa, if these variables were put in, then it would be able to draw that particular curvature. Polygons still represent the same idea, right? Where they have an x1, y1, z1, all the way up to an x sub I, y sub I, z sub I, some defined item. And you know, it can be very basic, right? Like we have this triangle here, which would be 1/2 the base times the height. And it would know that by calculating the coordinates of these points here. And then this becomes much more complicated, where it calculates this rectangle and then subtracts these circular quarters. And then getting real fancy, you'll see some form of derivative where it calculates the area of some function here. Right? Again, all based on coordinating each point, providing either a function or some specific formula to identify what those items are. So how do we leverage these? These geometric shapes need to have some text with them. So this is a snapshot of the university area in the city of Redlands, California. And there are some points here that are represented, because we recall that there's no specific dimension to it. So at this particular point, we place a pin with this cool little graphic that tells us something. Hey, this is an academic institution. And of course, we have the wonderful School of Business right here. Well, these are placed on a map using some location. In this case, we'll say it's a latitude, longitude. And that latitude, longitude has a pin placed at it, and then this label would be applied to that first pin, and then this label would be applied to that second pin. So how do we leverage these a little bit more complete, right? So this first part's very simple. Now we say, oh, well, this point belongs there, and let's give it this label. Well, now we can use some version of a line, right? So if we used the freeway here, and we're going to start at this Texas Street, and we're going to go to Orange Street. Well, this might be our x sub 1, etc., and this might be our x sub 2, etc. And we might see that represented in our table right here, where they're connected. This line right here is connected. This happens to be another label that it is the I-10 freeway or Interstate 10, and it's locally known as the Redlands Freeway. It's more formally known as the Christopher Columbus Transcontinental Highway. So we can say, oh, at this location to this location, we're going to draw a line, and we're going to say that it is part of the I-10 freeway. And we're going to call it the Redlands Freeway. Now, what if we added this new stamp, this timestamp attribute field? What is that all about? Well, if I am traveling and I can find the time here, and then that same point or that same vehicle crosses at timestamp 2, what do we find at that place? There's a mathematical formula that comes out of this. Well, let's look at our old maps. This is how it was done very commonly 10 years ago, 15 years ago. So many taking this class or many observing this video have used this exact method before. So here's a picture of an atlas in the Texas area, and we see the city of Van Horn. Here's Van Horn right here, and it is at this particular junction right there. Let's use a new color for this, right? So Van Horn is this color right here. Oh, that blends in. So use a nice purple color. So Van Horn, oh, we can't win for losing. Yellow. Van Horn is right here. And we're going to travel to Pecos, which is right, let's just say it's right here. Okay. We would pull out our atlas to this particular page, or our Thomas guide, another common term, and we would start at this pink arrow, right? Switch over to our red again. Would start at this pink arrow right here, and it's pointing at this intersection, and it's represented somewhere around right here. So city of Van Horn, and I'm going to go from the city of Van Horn to city of Kent. Here's the city of Van Horn. There's the city of Kent. And I'm going to follow along from one to the other. It's on the I-10 freeway. The distance is 37 miles right here. And maybe there's something to see along the way. I make sure I tell my kids to look out the window, and here is the Wiley Mountains, right? And I want to know that I am in Culberson County for some particular reasons, and I also want to know is there's a rest stop. So here's Culberson County, and boy, do I want to know that there's a rest stop available. You know. And this is line by line how we would do our directions. Right? Once we got to Kent, we would need to look at the next phase, right, which would be this segment right here. And we want to go from Kent to this junction right here. And so we know that we're going to go from Kent to that junction, and it looks like Gomez Peak is along the way, and Davis is in there. This is the county of Davis. We can see that right here. And the Apache Mountains is something to look forward to right here. Right, so we see the mountain range right here. So we're going to check that out. We could say that, oh look, there's another rest stop in there. If we wanted to add to our attributes over here. And we would say, okay, well look, there's another 10 miles. So there's my 10 miles. And so on and so forth. And then I would look to see that here's Pecos way over here. So I want to get this segment and this segment. And I would end up with a total of 84 miles. And this is statically how it would be done. Well, let's look at something perhaps a little more GIS-y, something you're more familiar with using computer software. So just putting in directions to go from, say, Van Horn to Toyah. Let's make sure that we have our highlighter, and let's highlight Van Horn, and let's highlight Toyah. So the computer directions, which are over here, they say, well, we're going to go from here to here. We're going to get on the 10 freeway at Broadway, so we're going to go from Broadway to someplace along the 10 freeway, and it's about 1.1 miles right here. Now, this part, you're welcome to calculate on your own. I just about calculated it for the sake of being helpful, but this portion of the road was running at about 22 miles per hour, and that's because I can travel 3 minutes in 1.1 miles. That's about 22 miles an hour. And then I'm going to stay on the I-10 freeway, and I'm going to go 67.8 miles, which is right here. I'm going to do it in 56 minutes, which gives me 77 miles an hour. And so I got on the freeway here, and then instead of going to this little segment right here, or even this little segment right here, I went all the way over to this one. So the GIS did some stuff in the background we'll talk about in a second, but it just mimics what was done on the previous slide, where it just added the segments together, right? And then we end up here in Toyah, and it was 0.6 miles. So the total was 69.5 miles, and we averaged about 70 miles an hour. So if you look at our items here, we have 37, we have 10, and we have 22. So if we add 37 plus 10 plus 22, what do we get? we get about 69 miles. Very, very close, right? So this static map is within a half a mile. But what does the static map not give us? It does not give us this valuable piece of information. We are creatures of time, deadlines, and having this piece is very, very important to us. So how does this work? How does it know that it's going to take 56 minutes to go this amount of time, or this amount of distance? Very peculiar. Well, here's what's happening, and this is a snapshot of the Redlands Freeway. And in the freeway are cut these circles. These circles are called inductive loops. There's a electromagnetic relationship that when a car drives over them, it disrupts it, and it does a timestamp. It says, oh, at this time, that magnetic field has been disrupted. So here's a call to the database. Stamp that now. Well, the computer has to know the order of these, because we don't know unless we tell it which comes first. So if we look at the car in the foreground over off to the right, we know that the direction is to our right, to the viewer's right. And so therefore the points go as follows: 1, 2. So now we have something that looks like x sub 1, y sub 1, t sub 1, and x sub 2, y sub 2, t sub 2. With these in our database, with these attributes, these timestamps, we essentially can assess velocity, because that's a change in position, as in from 1 to 2, in a certain amount of time, and that would be the difference in time from t1 to t2. And by simply adding a component or calculating what the length is, we can calculate how many miles it is. And then we can calculate the difference in time, or hours. So we essentially can put the length in miles over the time in hours, and we end up with miles per hour. So this is how it's generally used in a more complex scenario. This is something you may get on your mobile GIS. Oftentimes we call it a cell phone. Maybe it's a Garmin or a TomTom or some other version of calculating directions. We can link multiple segments. So if we did that for segment 1, which begins in Los Angeles, segment 2 goes to Covina, segment 3 in Pomona, etc., etc., all the way to segment 5, where we end up in Redlands. So I'm in Los Angeles and I want to drive to the university campus in Redlands. Here we go. Well, here's what it looks like. It looks like we have from 1 to 2, we have x1, y1, time 1, x2, y2, time 2, and we see this relationship right here. And if we continue to add those segments up throughout the entire journey, we end up calculating that it's going to be 62.9 miles from Los Angeles to Redlands, and it will take somewhere between 1 hour and 40 minutes and 2 hours and 40 minutes if I take this direction. Location analytics even provides some variability in the change of traffic speeds. So this location, this geography, this symbol of by line and curves can have its analytics, its traditional calculate this concept attached to it and given an image so that we can interpret so much so quick simply by leveraging what's already there. So we're going to explore this idea later on in the video series, and it will end up being a task you can take on your own, where we're going to combine spatial and tabular data sets. The importance of this is the freedom to create your own tabular data sets or to use data that you already have in your place of business or for other research or coursework with spatial data, whether it's points, lines, polygons. And generally what's happening is that the spatial component is built in. And when we get into the software, you won't always see the spatial component. This is really a representation of what would be there. And then we have the tabular part, the part that is something you can put in your table. You can record it. You can label with it. And really, your tabular data is your attributes, your descriptors. And there's no limit really to how many you can have. So let's kind of pause for a moment. We've been working with lines and directions only because those are common items that you're using GIS on a regular basis. Let's stop for a moment and kind of spread to a polygon. Right? Here is a polygon that has a series of polygons, I should say, that has a descriptor shown. So instead of being a point with a label, it's a polygon with a label. And this represents the United States. There's something going on that is identical to the line portion. It just throws some off because they're polygons, where we have this spatial part, and we're calling it latitude, longitude, but really this is a complex series, right? And it's drawing out these irregular shapes, okay? Because Alabama is not a straight line. It is not a typical curve. It's much more similar to a series of functions. And in a previous course, we had tabular data that we looked at population. We looked at male, we looked at female. And we want to combine these two. Well, what's happening is a one-to-one data relationship where the spatial aspect, Alabama, is looking for a match in the table. Once it finds it, it links up. Same with Alaska, Arizona, California, Colorado, and all the way through whatever is in your tabular data set and however it matches to your spatial data set. And the two just join up. So we have one cohesive unit. And this becomes something we can symbolize with, something we can work with, something we can map with, something we can make decisions with, and something we can communicate to others with.